Hello, we are the Unmanned Area Vehicle Cyber Defense Simulator Group, and this is our project. Okay, so a quick project overview. The project was to design a UAV cyber attack and defense simulation system. So in order to do that, we've created a simulation server which hosts ground control and a simulated drone, which each runs in a respective virtual machine. We've also created virtual machines for the offensive and defensive cyber operations. The offensive cyber operations are carried out by the red team using the Kali Linux attack box, and defense is carried out by the blue team using Snort or Security Onion or some of the other instances that we've created for that purpose. So here we have two block diagrams. The one on the left is for a physical drone. This would be if we actually built a drone that conformed to the drone code standard. And the one on the right is our simulated drone. You can see in both cases at the bottom, the external communication with the drone is via a ground control station. For the physical drone, that would be a separate laptop or tablet. In our case, we're using the ground control virtual machine. But they're both running ground control software, and for this case, where they're both using MAV proxy as that ground control software. And they're both communicating over MAVLink over Wi-Fi to the drone itself. For the physical drone, that signal goes to the drone processor, where it's running the MAV proxy software and also various other applications of the MAV proxy software is communicating over UDP. In our case, for the simulation, we're just using a Linux terminal to run the MAV proxy software, but again, it's the same software. And then MAVLink over USB communicates in both cases to our ArduPilot software. For the physical drone, that's in the APM autopilot. In our simulation, it's running in a Linux X terminal. And then, whereas for the physical drone, that autopilot software is communicating via pulse width modulation to the airframe motors and sensors. For our simulation, it's communicating with our flight simulator, which in our case is JSP Sim. That's providing that feedback, location, and orientation signal back to that autopilot software. So what I've done so far is create the drone simulation environment. What this is a drone simulation server. It's just a physical computer server. It runs a headless Ubuntu installation, and on there we use as a hypervisor virtual box. And inside the virtual box we have 4 or 5 VMs. Right now we have a drone VM, a ground control station VM, a red team VM, which is for the offensive cybersecurity operations, and a blue team VM, which is for the defensive cybersecurity operations. And all those VMs communicate over both Ethernet or USB Wi-Fi adapters to our drone network router, which connects all those devices. And that's a physical router external to the server. Additionally, our drone simulator server is running a web server, which is Apache 2, and through that it's hosting PHP VirtualBox, which is our web application for controlling that hypervisor. We also have a remote desktop connect server, which allows us to remote desktop connect from the internet to any of those virtual machines. And we also have an SSH server, which allows us to get a secure shell connection to our server machine for applications. And then we have our internet access point router, which is what allows us to communicate with the internet so that you can manipulate and control any of the aspects of this simulation environment from any internet connected device using a web browser and a remote desktop connect application.
Hello, my name is Clarissa Gonzalez and I am part of the Red Team. So for the Red Team, we were tasked to research different penetration testing platforms that can be used for attacking Wi-Fi connections, drone control software, Linux operating systems, and controller computers. After we did our research, we needed to select offensive tools and develop knowledge and skill in their uses. Some of the attacks that the Red Team wanted to accomplish were Wi-Fi deauthentication attacks, IP MAC address spoofing, cookie stealing, session hacking, DDoS credential escalation, and man-in-the-middle attacks. We chose to work with Kali Linux given that it's the most advanced and versatile penetration testing platform. It's pre-installed with over 600 penetration testing programs, including port scanners, packet analyzers, password crackers, and penetration testing for wireless LANs. Kali can be either installed on your computer's hard disk, it can be booted from a live USB or a live CD, or it can also be ran within a virtual machine. Knowledge about this platform was crucial for our team to be able to manipulate attacks. Once we started to become familiar with the tools within Kali, we intended to break the link between the drone, and the ground control system, as well as overpowering WPA encryption. So for my research, I was able to become familiar with IP and MAC address spoofing. Using these attack methods are extremely beneficial for the red team. Using IP spoofing allows you to hijack by pretending to be a trusted host to conceal your identity, hijack browsers, or gain access to a network. So for our project, this is extremely crucial and beneficial since both the drone and the ground control station have IPs that can be spoofed for the attacks. The IP address of a valid host can alter the packet headers so that the valid host appears to be the source. Therefore, it causes the drone to think that it's communicating with the ground control station when in fact it's not. Using Kali Linux for Mac spoofing was relatively easy. There was different ways to accomplish this task. You can either have the MAC address automatically populated for you, or you can choose a MAC address that you would like. The only requirement for this is for the MAC address is that it needs to be 17 characters long in hexadecimal format. Being able to use this tool for the attacks was a key because we wanted to we want these attacks to occur under the radar without the drone or the GCS being able to track the local network or our hardware. Hello, this is Clarissa, and I've been assisting with the testing for the red team. Before testing was conducted, familiarization with the VMs that the red team uses for attacks is crucial, such as Kali Linux, the GCS, and the UAV to be able to execute attacks. The attack method that I tested was the man-in-the-middle attacks, which is taking over the UAVs by using Kali Linux and the Python scripts that were created to take over the UAV. For the man-in-the-middle, we're testing to see the success rate on how successful we were, or I was, in sending a command to take over the actual UAV. As far as future work is concerned, the red team just wants to make sure that we're incorporating our attacks with the blue team and the defense tools that the blue team come up with, that we can attack the different tools that they incorporate, and just adjusting our attack methods as needed.
Hi, my name is Zach Tyndall, and this is the Red Team. The fundamental ideas and tools from the Red Team are listed here. It's basically just to know your target, to monitor your target, and to gain information that gets you access to the target. And our target in this case is the UAV and the GCS, and that sort of relationship between them. Some of the tools that we used are on the right. Those are some of the tools that we researched, and they do just various things as far as information gathering, and we use these techniques later on down the line. On the simulation side, the goals were to just demonstrate the UAV being attacked in this virtual environment. The challenges to that were working in the virtual environment, using various methods. We were able to overcome those challenges. And the methods I'm talking about are using IP forwarding technique that I discuss later, as opposed to just simple deauthentication of a wireless network. This is because within the virtual environment, an Ethernet interface is being used rather than the wireless interface. The process of attacking the UAV starts with the target analysis, and what we were looking for were the IP addresses of the GCS and UAV, as well as the port of the GCS. Shown in the bottom, we can see that there was actual results using SCAPI, showing that there was a virtual connection between the two, and they weren't on the same computer, and they were communicating between the network. What could help to analyze all of this is just to know the specific range you're looking for before you even start the analysis. The actual taking over of the UAV is done by initiating the attack by starting the script, and the user sends the IP address of the GCS and UAV, and it gives it the interface. Then the automation begins with IP forwarding on and off, which severs the link between the GCS and UAV. The UAV is then fooled into thinking the Kali box is GCS via ifconfig network settings. MAV proxy is then used to send commands to the UAV, and a no-link status is given to the GCS.
Testing for the red team included subsystem functionality, as in the inherent functionality of Kali Linux and its situation inside the whole simulation, and that's where subsystem interaction comes into play. And to test that, we use the man-in-the-middle method, as in inserting ourselves in between the GCS and UAV and picking up traffic, and that way we could test whether this system was actually connected, and we were able to test attacks after that. We did denial of service tests and arbitrary command tests. The denial of service test was using the low orbit ion cannon, or it's just basically flooding traffic into the network to prevent communication from the UAV to the rest of the network or the GCS, and it was just flooding their network traffic with ARP requests and stuff like that, just so that it loses connection. The arbitrary commands is somewhat similar to the man-in-the-middle, except that there is no insertion there. You just capture a command from the GCS to the UAV, and you wait, and then you rebroadcast the command, and you test if that worked by seeing if the the UAV actually followed the command. And if it followed the command, then the test was a success.
Future work on the project includes automation, interaction, and stealth. The automation and interaction are mostly centered around the user interface, where the user might get options for a target after specifying maybe a range to the script. The stealth base is basically fooling the GCS into thinking the UAV is still under its control by using the no-link status. Kind of gives away that the drone has been taken over. At the bottom are the demonstration videos. The first one is the Kali demonstration of the tools. The second one is the demonstration of taking over the UAV. Thank you.
So the final version of the blue team's intrusion detection system contains 4 key components. The first one of those is Snort, which is our network sniffer application. It is monitoring all network traffic. Every packet sent across the network is viewed by Snort, and it compares that traffic to a set of rules that generate alerts if the traffic is viewed as a potential security concern. We're using Snorby as a GUI to evaluate those alerts. Snorby goes in and will show you every alert, what its title was, the rule associated with it, what time it occurred, how many of what type of alert you're getting. Every method you could choose just about to monitor and evaluate that potentially dangerous traffic on your network, you can go into Snorby and see. We also installed ARPWatch, which is able to take a look at the ARP file, which is a network file that lists all the MAC addresses of devices on the network and the IP address it's paired with. A lot of the man-in-the-middle attacks and ARP poisoning attacks will modify this ARP layer so that the attacker is able to appear to be a friendly system. So ARPWatch goes in, it takes a snapshot, so to speak, of the correct version of that ARP table, and then looks at it periodically from that point on to detect changes in it. And we've got that looking for any new systems on the network and any IP address changes or IP address mismatches, which is where a machine is broadcasting that it is a different IP address than what it's actually configured to. The final component that we're running is Swatch or Swatch Dog, and that is a log file monitor. So it's looking at the snort logs and it's looking at the syslog, which is where ARPWatch writes its alerts, and it will take any predefined action based on the search strings that we assign to those log files. We have 2 instances of Swatch that start every time the system loads. One to look at the snort alert log file, and one to look at the syslog file. All right, right now we have snort running on the system, and the snort rules are maintained automatically through the pulled pork application. Anytime a new set of rules files is posted to the snort community, the pulled pork application will download those rules and put them in the correct folders, and the next time snort starts up, it has those new rules available to it. So snort is running on the ETH1 adapter, and ARPWatch is running on ETH0. The two are not able to use the same Ethernet port adapter, so the blue team IDS system had to have 2 adapters set up, one for each application. ARPWatch is monitoring for any IP address changes, which are listed in the alerts file as a flip-flop. This is what we had noticed, that the way we've been running the attacks, the man-in-the-middle attacks and the denial of service all come up showing as a IP address flip-flop. So that's what we've got it alerting on. Obviously, ARPWatch is monitoring the entire ARP file for changes, so it's also detecting the new devices. It would detect an IP address mismatch if there was an issue there, but the one that we're actively looking for right now is the flip-flop. Swatch is monitoring the snort log file and syslog, which, as I mentioned, is where ARPWatch writes its alerts to. Swatch is looking in both of those files for certain strings that we've set up in the snort configuration. Swatch is looking for priority 1 or priority 2, and then for the ARPWatch, it's looking for that flip-flop tag. And then once it gets those, it sends out the return to launch command. That's written into the config file as well. that has to be, those config files have to be updated every time the UAV and GCS pair to make sure that the correct IP address and port numbers are in the return to launch command string. What we found is that the port of the UAV is randomly established during the initial pairing, and so after the GCS and UAV have been paired, you have to capture some traffic between them to extract the port of the UAV, go in, edit the config files, and restart the program, the swatch programs, or just reboot the system to make sure that the return to launch is going to actually be recognized by the UAV, because even if it's sent to the correct IP address and says it's from the correct IP address, those ports are important too. So that has to be in the body of the command. So we have to rewrite that every time to make sure it's going to go to the right place. In addition to that, we also had to make some changes to the Linux sudoers file. This is a master file that allows, or that gives permissions for things to be run as root or sudo without requiring the password to be entered. We did not want the return to launch command held up waiting on a password. The goal was for the IDS box to be able to run more or less independently during the entire flight and kind of automate these responses. So that file was edited to allow send IP specifically to be run without the password. For the initial testing of the intrusion detection, I set up the ground control station and UAV to perform normal missions and had Snort running during all of this, monitoring the output of it through Snorby. And I ran 10 full missions at about a half hour each and was not able to detect any false positives, which was one of the key parameters. We didn't want to have the UAV sent back to the launch location without an attack actually having occurred. The next thing I tested was that we were going to get the correct response if we did get a priority 1 or priority 2 alert. To do that, I wrote a local rule that was just looking for an ICMP traffic, which was a ping, and initially I assigned it as a priority 1 in the rule, and then I set up the system and pinged it from the host computer. Then using a sniffer program on the host computer, I looked for the return to launch command being issued by the IDS system, and that was detected. I repeated that at a priority 2 level to make sure we would get it for both. Same response. So Swatch was working, it was sending out the correct response using the send IP, and we got the expected responses there. Then after that, still on the hosted system on my private network, I used ARPWatch to monitor the system for a while, and then I went in and verified that it was able to detect a new wireless device that I had connected. I put a new printer on the network and was able to go into the syslog file and verify all of those alerts were logged, and had Swatch been looking for a new device alert, it would have issued the command, but the Swatch file is actually looking for the flip-flop that indicates the man in the middle attacks. So the baseline testing of all of the IDS components passed.
This is Joshua Fredericks for the UAV Cyber Simulator project. I was on the Blue defensive team. The beginning of the project, I began working with Security Onion to research IDS and IPS tools. But with researching those, we found that it was a good tool to learn about them, but wasn't really customized to the needs of the project. So a decision was made as a group that we'd run just a standard Ubuntu Linux virtual box with Snort running on it, Watchdog, ARPWatch, and the overall defensive plan was to use those tools and then have a honeypot as an initial defensive layer to hopefully to confuse and deter any attacker. The honeypot was based on the send IP tool. Generates false traffic to delay attacks and hopefully allow for Snort and ARPWatch to alert on any attacks and implement defensive measures. I also use the watch command in Linux to create some randomness with the send IP, and Zach created a bash script to encapsulate all the different send IPs to make it more user-friendly and efficient. Wireshark was used to read packets that the UAV and GCS were sending each other and then determine their meanings. So with some testing on the different packets, so I would use a send IP message to send different packets. I was able to determine what their actual intent was, if they were a return to launch message, a mode loiter message, a mode land message, etc. And then using those messages, I could recreate the traffic using the send IP messages, recreate the traffic that a normal GCS UAV would create. To test the honeypot false UAV GCS traffic, I took a sample size of 10,000 packets from the GCS UAV, and then I did the same with the honeypot. So I took 10,000 packets from them and analyzed them. The primary tool I used to analyze them was the statistics tab in Wireshark. I think that would be more realistic of what an attacker would do. So they want to quickly be able to analyze and determine, hey, which one of these is the actual GCS UAV and which ones are fake. So they would probably just use those immediate tools in front of them. With that, we were able to get fairly representative response. So I believe it was about 85% accuracy in the packet length and about 95% accuracy in the rate of packets sent. And that was deemed sufficient enough for the purpose of this project. You could try to get it closer, but there's really no point in getting 100% duplication, because if you were to take any 10,000 set sample size, it's going to be different from the actual GCS UAV. So depending on what mission you have them doing and what types of GCS UAV they are, you might have a different pattern of traffic. So we just wanted something that would represent what could be seen as legitimate traffic. We did find an issue with the simulation environment, the honeypot in the simulation environment, due to using the ETH0, the wired connection in the virtual manager. So it doesn't quite work out as you would expect under a Wi-Fi network, but we think that's acceptable considering the constraints of the simulation environment and the project.
During the initial testing of the attacks against the unprotected UAV, the man-in-the-middle attack was successful 100% of the time. Because of the way we were doing this with the wired setup and the red team already having the IP addresses for the UAV and GCS, it was pretty much just a go in and do the attack. So that succeeded 100% of the time. And the rebroadcasting attacks were successful about 96% of the time. When we went to do the final testing with the blue team's defenses in place, the honeypot and snort were not a factor in this because of the way we have the system set up right now. Snort's not able to detect any sort of intrusion attack because the red team really isn't using one right now. They're just connected and starting the man-in-the-middle routine. So the only thing that was really being tested here was ARP Watch and the Swatch response to those alerts that ARP Watch would issue. Unfortunately, there were some issues. The config file for Swatch did not get rewritten with the correct port address. So in all of the testing, we didn't see the return to launch command. However, going back and looking at the log files, we were able to detect initially when the red team connected. You can see in the first alert line I have here, the news station connected on at IP address 128, and then it changed over to address 113, and then from that point you get flip-flop alerts on the 113. It goes back and forth between a couple of the different MAC addresses as the man-in-the-middle attack occurs. So there were pages and pages and pages of flip-flops as it would go from the one device to the other, as the actual GCS would be sending something, and then as the red team's VM was sending it out pretending to be the UAV. So had the Swatch configuration file been written correctly, the return to launch command should have been sent, because the triggers were definitely showing up in the syslog file. So we were able to detect 100% of the attacks, but we didn't see the return to launch that we were looking for. With a little bit more time and a better setup for testing, we probably would have seen the results we expected. Unfortunately, with only one team member really able to log on and do this, we were trying to feed each other information, and some things got missed. So moving forward from here, one of the first steps would be to implement the VMs over a wireless network instead of the wired setup that we were currently using. This was too hardware intensive for us to get accomplished this year, but it would allow the effectiveness of both the honeypot and the snort intrusion detection to be adequately tested. The honeypot is there to confuse the attackers, and when they're wired in and already know the IP address and not trying to actually locate the target, that does no good. And snort does not see a computer connecting through a wired connection to be a threat to the network. That's normal network activity. So there were no security alerts generated by the red team in any of their attacks. We were able to detect the man in the middle and the rebroadcasting attacks through ARPWatch. However, the way we had implemented ARPWatch was to monitor the syslog for the ARPWatch alerts, and then we monitored those using Swatch, and then had Swatch respond to them by sending the return to the launch. That was kind of cumbersome since ARPWatch is open source. A good step might be to modify the ARPWatch code to be able to send the return to launch command. You would still need to develop some sort of file or edit it every time so that you could get the correct IP address and port information in there every time the UAV and GCS pair. But it would be one less piece of software to potentially have problems with. Then, of course, we need to at some point integrate this with actual drone hardware to test the response of a actual UAV. Thank you very much for your time today.